Hello everybody and welcome back for our second presentation of the afternoon. So just a quick reminder, everybody who's joining for the first time, please use the chat to introduce yourself, tell us where you're joining from and what time it is. Our speakers will be online during each session, so if you have questions, feel free to fire them through the session and they'll be able to respond in the chat. Or if you have a question you'd like to keep for the end, then use the question mark tab and submit your question that way. Okay, so on with our second presentation of the afternoon. We have Alexander Noack of B+. Over to you, Alexander.
Welcome, everybody. My name is Alexander Noack. I'm the head of the Product Center Automotive Electronics here at B+ in Germany. Today, I would like to talk about a topic which is very interesting for those guys working on AI topics in general, and especially in the field of autonomous drive developments. So the topic today is how to harvest reliable AI training data for sensor function validation. I would just briefly introduce B+ to you if you want. Well, basically, B+ is a company which is founded like 1996. So we are a 24 years old company with 250 employees right now, located in the very south of Germany. So in a beautiful area down here, just an hour drive away from Munich. The focus of the company is basically working along with the tier ones and OEMs and some technology companies in the field of ADAS sensors, where we started from, as well as autonomous drive developments as such. Well, looking into autonomous cars in general, and there's a lot of stuff going on. So I just put some pictures out there, which basically give a bit of an overview of what is happening in this field. Recently, due to the COVID-19 issues, of course, some of those activities have been delayed or stopped. But in the end, all the major tier ones and OEMs, as well as some technology companies and some very good startups are working in this area in order to address a market which is down the road for a couple of years still to go, and we'll see things coming up pretty soon on the roads. We also see them already on the roads, and the basic technology around that is a lot of sensor stuff. We will see that in a minute, but as well as that, a few years ago, companies started to just bring up some examples for so-called autonomous drive platforms. This goes back about 2 years now, and the examples I have in here is not really most recent up to date. There is more things coming up now. There have been things being delayed or taken away again from the market. But anyway, these kind of technologies are out there in the market. Well, looking into autonomous drive platforms as well as autonomous cars, the major thing which is relevant for the autonomous drive development is the sensor equipment. And I have a sample configuration for you here. Well, this is basically a sensor set which we have also mounted in one of our test cars over here in Germany. And we work with a set of cameras and radars as well as some lidars on that. And this is quite common to all these kind of cars you have seen in the previous slides. There's a lot of sensors for the environmental detection, for the cognition of the environmental model. Well, and once we look into that, there has been a lot of development going on, especially in those sensor fields. Once I look back in 2000 and 2001, where we started to work with the first camera developments, we had like, considering today's raw data sets, we had like very little amount of raw data. Nowadays, if we look into this example setup, we have 6 cameras and 6 radars on this car. Looking into that, it's like 58 terabytes per 8-hour test drive shift. So this is a lot of data which is generated there. Not all of that is really relevant for the training of artificial intelligence at the end of the day. But in the majority of cases, our customers tend to capture as much as possible data in order to have the right data sets available. Well, looking into that, it has been a lot of discussions around the amount of data being generated. There's a lot of discussions around what kind of resolutions and how many of those sensors are necessary to really do a reliable and safe autonomous drive platform or autonomous drive vehicle at the end of the day. But what is common to all of those is basically we are now talking about a data-driven development, looking into more like neural networks, artificial intelligence, machine learning, all these kind of topics which are in common, of course. They need accurate data for the training of those models, for considering various scenarios, find out corner cases, get enough overview on weather conditions, traffic situations, and all these kind of things. So there's still a lot of classic, let's call it algorithm development going on, but a lot of things now happen more and more in the field of neural networks and artificial intelligence. And for the purpose of that, we need to consider the logging, which seemed to be a quite easy task in the past, now from a completely different kind of standpoint. Because what makes reliable data reliable? Putting that into a nutshell, what are the challenges when dealing with these kind of multi-sensor source data? Well, we need to look into various sources which need to be time synchronized and sorted accurate. So this means once you have a traffic scenario and you have a camera and a few radars capturing the situation, you want to make sure that all this data is in line with the training model in order to get the proper results for your artificial intelligence training. Well, no data must be lost. So, which is all the frames we get from the cameras, all the frames we get from radar front ends, all the information we get from lidars must be in line, and no packet has to be lost at the end of the day. However, as things happen right away, if there is a packet which is corrupt, if there is data which is corrupt, it has to be marked properly and put into the chain for analysis and replay and simulation at the end of the day. Well, these are the challenges we are dealing with, and these are the challenges we are looking into, especially in this talk. Well, to give you an overview on our general way forward, I've put some pictures together, which is kind of a, we call it round trip for the development and validation of those systems, no matter if it's a camera, a radar, a lidar, or even a autonomous drive platform. We start at the very left, let's say, with a software or algorithm development team, which is working on a pretty early stage of sensor set or a autonomous drive functionality. Well, we put data into an ECU, we generate ECU software. This is something our customers do with the help of our team. In some cases, we work directly in the ECU software development. As soon as we have that in place, a lot of test vehicles are being equipped with these kind of software sets, software stacks in the end. And during the test drives, we capture an enormous amount of data. We have seen the number of 58 terabytes per day per vehicle looking into this kind of raw data streams. Well, we put that on top of drives. Of course, it's not hard drives anymore. It's more like flash drives sitting inside the vehicle, transferring that through a different way into the cloud or through any kind of LTE connection or whatever, of 5G, 4G, whatever it is, will not be possible with this amount of data. So we store it locally. However, we still use connected services for pushing meta information into the cloud, getting information from the vehicle as fast as possible into a fleet manager scenario, or even into the development sites of the customer. The majority of data is coming into a truck, a forwarder, whatever you've seen. You could see that on the picture. It goes into the premises of our customers, to the ingest stations, and from there it goes onto their data centers, and in some of the clouds in the world, also a lot of those data is ending at the end of the day. We call that phase the analysis and simulation part, because this is where a lot of tagging, a lot of data assurance with the data sets is happening. as well as a lot of pre-processing or post-processing is happening. Because what we want to take at the end of the day is real-world data, which is able to be fed into systems for testing, for further testing, as we call it, hill tests over there at the left corner. And once we have that in place, we can do a combination as well of real-world data, which we have captured on the road, as well as simulated data coming from any kind of simulation frameworks. This ends up in hill or sill or even vehicle in the loop testings. And at the end of the day, the feedback loop is closed to the software and algorithm developers. So we see that in plenty of times. It's always kind of the same approach to that. Of course, looking into classic algorithm development versus AI training, there's a significant difference. But the majority of data needs to be ordered in the same way. So that's why we want to take that as an example for what is happening out there. Well, just a brief overview again, putting that into a nutshell, what we have seen. We do data recording. Test fleets are collecting real environmental data. On that side, we need to take care about data decoupling, which means all the proprietary interfaces of sensors, all the raw data interfaces of sensors need to be put in the right way. We need a chronological recording of all sources. For that, of course, we do a clock synchronization and timestamping on each of the packets. And additionally, of course, we want to monitor the data integrity, which makes sure that no packet is lost, that data isn't corrupt, that data are captured at the front end of the sensor will also be the same data set which ends up on the disk or even on the data center. Well, in some cases, we do data processing online, which means in the vehicle, a setup is being generated for that. Well, we do data quality assurance and enrichment over there. And many of our customers are working in the area of analytics and scene detection. So they want to capture specific scenes rather than the whole story of the drive. They want to do data enrichment, automated labeling, or even live processing of the data. Once this is done in the vehicle, the data is ingested in an upload station into the data center at the edge of the data center. Well, in this case, we need to take care of the transfer from the test car to the data center, copy all sources via a copy station or a storage unit or whatever it is, or a direct link into the cloud. And we secure that with hashes in order to make sure that all data is ending up in the right way and we do not lose any data during copies. Well, how is that setup being generated in the vehicle? You have seen an example earlier in this presentation, and I want to just step by step go through that, where it started from and what the essence of this kind of recording scenario and recording setup is. Well, at the beginning, it's a camera, let's say, which customers developed. This was a starting point also for our company. And with this kind of developments, we basically worked a lot on the sensor level. And nowadays, of course, we take that sensors, which usually are sending out an LVDS or serialized signal. We convert that with these kind of interfaces into a generalized 10 gigabit Ethernet link. And at the end of the day, it ends up on one of our recording setups or one of our recording systems, where we store that data locally on one of those cartridges, which sits on top of this device. Well, usually the most critical path in this case, and what I considered earlier in terms of time synchronization and securing the data or data integrity monitoring, how does that work? Let's have a deeper look into that. Well, a simplified view on this device is pretty easy. You have an interface on the left side, which is capturing the serialized signals coming from the sensor front end, no matter if it's camera or radar. We do projects on both of them. The main thing around that is we first of all have to get the data into the system using a deserializer setup. Once we have done that, data is being forwarded internally, of course, and every packet is time-stamped. So every of those packets now has a timestamp. We still need to check integrity, so we put CRCs on top of that as early as possible in the chain. Once this is done, all the packets are put together in larger UDP packets, and at the end of the day, it runs out to the recording setup, to the recorder. Well, putting some additional sensors into that is quite a simple task in this case. So basically we just add them, we connect them to the recorder, and we can record that data additionally. Usually this is not enough for a test setup, of course. In many cases we have to add radars, no matter if it's near, mid, or long range radars. Well, we put a set of radars in there. In this example, they're connected through CAN interface, so they basically send out object lists, and we capture this through the CAN interfaces. Well, together with the camera, the LiDAR, and the radar, we get some good picture already about the environment in these specific scenes. However, this is still kind of a very easy setup. Well, let's add additional cameras into that. What does it look like? Well, we need an additional measurement interface. Yes, we still have one recording platform, which can store up to 64 terabytes at a maximum. And with that, we can really stand one day recording easily with this kind of, let's say, simplified setup. Well, if we need more, we're just adding more cameras. We add a new second recorder. Once this is done, we also have to make sure, okay, we need to put the time in correctness, which means all the recorders need to have the same time basis. And for the sake of data distribution, we put an additional switch as well into that. It's not really mandatory for that, but we'll do it in this setup. So once we have that in place, we have a time-aware switch. We have 2 recorders, we have 6 cameras, we have 6 radars, we have 2 LiDARs. So it's pretty much what we saw in the example earlier. Well, now we have this test car being equipped with a recording setup. It works pretty well, of course. But however, there is some kind of maintenance or some kind of remote access being desired by many of our customers. So we add an additional component, which is fleet management connectivity solution, which enables updates over the air or a remote monitoring of the car, the equipment inside, the measurement equipment especially, putting new configurations in there, whatever it is. A driving campaign management, send out messages to the driver, is also in there. So we add this layer for the connectivity. Well, I talked about this topic like online data handling inside the car for the sake of algorithm prototyping or drive scene detection or automated labeling. Well, for that purpose, we put an additional node into this kind of setup. The node is a compute node, a very high powerful PC platform using multiple GPUs and multiple CPUs. No matter what the requirements are, this is all configurable, of course. And now we have a very good recording setup. We have a decent compute unit in there, so we can do a lot of things in the test vehicle, running the data. We can even use the data already for AI models inside the compute unit because we're running GPUs in there. So we can add some functionality even in the very early stage of a development phase for the algorithm. Well, now we have 2 recorders, a compute unit, and a connectivity device in place. Well, we might want to have a central point for storing all the data. So we basically add a mobile data lake, a so-called MD lake on our side, which is offering the highest performance with 128 gigabit per second. And it also reduces complexity during the recording and during the ingest at the end of the day. Well, adding that on top of that, this really completes the setup in terms of the hardware layers we have in this kind of scenario. Well, of course, there's an additional use layer, we called it, for the software running on all these different devices, for handling the big data streams, for capturing or sorting the frames coming from the various sources, or even offering a clustered recording service, which means all of those recorders do have one trigger for recording, or they have an automated trigger for recording no matter what. And it's being stored on the devices. The handling is quite straightforward using a tablet for the driver, for instance, or using the software on top of any kind of device over there. Well, it's really a flexible and tailor-made setup. So basically all the Aveto measurement setup, we are calling it here, is flexible, modular, and future-proof. So you see, you can start with a small setup. You can even extend it over time because this is a usual approach. There's more sensors coming in, and these things are growing. Well, at the end of the day, many of our customers do have components in place which they want to reuse. Of course, they have invested a lot of money for maybe a recorder or maybe a custom-specific sensor or a software tool set which they are used to work with for a long time. Well, this is not a problem at all because the flexibility and the modularity of the system gives a lot of chances for integrating like custom sensors, like integrating recorders from third-party, even getting away all the recorders and use third-party devices over there, and still integrating a switch or a mobile data lake or even the compute unit. And of course, there's a lot of software tools out there which are used widely and which do put together all the things at the customer at the end of the day and integrated in the customer's development chain. So it's not really easy to change that. So also there, we do have flexibility to really integrate that. Well, at the end of the day, we have captured all of this data, and now we need to take care about how does it end up in the data center and how does it work with training that artificial intelligence network. Well, if we look into that setup, we basically approach the data centers on an edge node with these kind of, we call them copy stations or copy links in this case. Those devices are at the edge of the data center or even the co-location space. And we had some talks around that as well with some data center providers like NTT, and we work a lot also with guys like IBM and such. So there's a close link to also those data center and IT guys over there. And well, if we look into that, the classic thing would be, well, we take out those cartridges, we bring them into the data center, and we copy them to the data center's servers. Well, the good thing with this mobile data lake is that, well, we don't need to take care about multiple of those sources. We just have one device, which we either take out of the car and bring it to the data center, or we have a 100 gigabit Ethernet connection going into one of those copy devices, and from there on, the data ingest is happening secured through hashes, of course, into the data center, into the servers. From that on, this is where I always call it the magic happens. So the data is being processed there, the data is being tagged, meta information is enriched, all these kind of things which are happening in the data center or even in a cloud environment. There's a lot of players out there also offering that. At the end of the day, the data which is being enriched over there is being used, as I mentioned earlier, for the training of AI models, or even for a classic kind of corner case tests in a classic algorithm development. Well, once we have all that done and the model is trained, or we have developed our own algorithm, or the customer has developed this algorithm, finally, we go back into the vehicle and put that onto one of those drive platforms at the end of the day, for instance, for providing a drive functionality, or even an intelligent camera, or a LiDAR setup, which has additional functionality. So once we look into all that, basically, we have seen that the setup looks quite complex. However, it's made for integration of third-party components. It's made for using a technology which is given while we do everything on Ethernet, which is possible. And we use Ethernet time synchronization topics. So there's a really good way into technology which is given in the IT world. And it's a seamless integration into the IT world. Looking into the car or into the data center, we do combine things there. Well, once we look into that as a summary, and this is the end of the presentation basically, we have to think about a global and flexible time concept for gathering reliable data. We need a flexibility in such projects, which ranges from 1 gigabyte per second, where we started like 4 years ago with this kind of mark. Now we talk about 16 gigabytes per second, And we also see that customers may not want to store 16 gigabytes per second permanently, but they have the majority of sensors providing this kind of bandwidth. So for a given time period, they need to sort of store that 16 gigabytes per second. And this is what we then call intelligent logging. So this means with these kind of AI topics inside the vehicle, you've seen the compute unit, for instance, you can even understand what data is coming in, and you can get your scenarios being captured the way you want them to. Well, we do the check for integrity of the data transfer in every step, even up to the cloud upload or the data center upload, and we flag the errors during the recording. Well, basically, this was the overview I wanted to give you in terms of AI training data and how to get the reliable data out there, and what is the complexity of these kind of setups, and what is the ease of integration of third-party components, and how modular is the system. Well, thank you very much for your attention. I hope it was interesting for you. And well, at the end of the presentation, we will go to questions and answers. Thank you very much.
Excellent. Thanks very much, Alexander. Very nice overview. Very interesting presentation. Good afternoon. So yeah, we've had some Q&A in the chat. I've seen you've been responding there. We're running into the coffee break, but that's fine. We'll take time for a couple of questions. Do you have anything you wanted to add verbally to the responses and the discussion in the chat?
Well, there were some things being discussed, and mainly one of the questions also was coming out of the area of, let's say, production autonomous drive vehicles. Mm-hmm. And just wanted to point out that the topic I showed is more like focused on the development side of these things, but some of those parts, and this is why I emphasized the modularity of the concepts and the technology we are using, which is quite some kind of standardized, looking into Ethernet and time synchronization topics. Mm-hmm. This can be, of course, transferred into some kind of project-related topics around also, let's say, production cars at the end of the day.
Mm-hmm. Mm-hmm. Yeah, no, that makes sense. So you've talked a lot about synchronization. That was a topic in the discussion as well. That's being one of the most important topics. Can you tell us a bit more about the method that you use? Is that a proprietary method?
Well, it's not a proprietary method at all. We basically use a standard method coming out of IEEE 1588 standard. Okay. So Ethernet time synchronization, and the profile which we use is 802.1AS, which comes out of the AVB standards, which was widely discussed. And we have some specialists working in these working groups, joining those specifications. So we are quite at the edge of their kind of next specification levels.
Excellent. And you showed a device called MD Lake as a central storage point. Can you tell us a bit more about that?
Well, the MD Lake is a pretty new product which we just launched earlier this year. And basically, this is the clear strategy we have to really use kind of technology also inside the vehicle, which is known from the IT world, because we look into very, very large amounts of data, very low latency requirements, and a very high density of data storage. And this is why we made this mobile data lake using data lake technology from the IT world, converting that into a package which can be used in those kind of test cars.
Okay, thanks very much for that information. Thanks for joining us for the Q&A and for your time to prepare the presentation. Very interesting, and we'll look forward to hearing more from you at a future AutoSense, I'm sure.
Thank you very much, Rob.
Thanks. Okay, everybody, so that takes us to the next coffee break. Please take some time to discuss the proceedings today with some colleagues, and we'll be back in around 10 minutes for the next session. Thanks very much.